Alright, so let's get into actually managing the data in R. The first thing that we want to know how to do is to save and load data structures. So in the last part we did save the CSV file, but let's create three objects. X, let's give it the number 1, Y, let's give it 2, and Z, let's give it 3. Sorry, 3. Sorry, here we go. And so we've assigned these three objects these three values. Now what we can do is we can save these objects to recall later. So we can use save x, y, and z, and we can write a file called mydata.r. So we've saved this file. Now this is so say we'll remove these three objects. So the environment is empty. If I wanted to load these objects later on, I can use load, and the file name would be mydata.r data, and I hit enter, and as you can see, XYZ have come up as well. So let's remove those again. Alright, so now let's just a warning with the loading of the data of X, Y, and Z. That'll get rid of your current X, Y, and Z in your environment. So if you're working on something, be sure that you actually know what you're loading up, and be aware that you could lose that, whatever you've been working on, if you have the same variable names associated with that. Okay, so we wrote the CSV file earlier, pt.csv, and we can actually load that by using read.csv. CSV stands for comma separated values, where the comma is the delimiter. So again, strings as factor equals false, and we can read that data earlier, and that's because the working directory wasn't set to my current working directory. So what you can do is you can set the working directory to the directory is equal to whatever your directory is, and you can figure it out wherever you're working out of, and set the directory to where you actually saved your stuff. So I'm going to skip the part about the SQL databases. You can read that on your own. I'm going to skip to the used car CSV. So we're going to load this used car CSV, and let's look at what it actually is. So we have the year, the model, the price, the mileage, the color, and the transmission. These are pretty good variable names, and you can figure out what is basically happening with these cars are probably for sale. The one thing that is a little unclear is the year. Is this the year that the of the car model? Is this the year that it was listed for sale? So we don't know that kind of information, and we're going to have to examine. If we don't know that information, we're going to have to examine the data a little further. So the first function we're going to use is str, which will give you the structure of used cars. So let's put that in, and let's look at the actual output. So we have 150 observations of 6 variables, and it gives you the types of each. So you have the integers for these, the characters for the model number, the prices, the mileage, the color, and the transmission. Now we can start understanding a little bit more about the actual data contained within the used cars. Let's use summary to get some useful statistics. So it breaks down the variables year, model, price, mileage, color, and transmission. So now we get a little more information about the year. We see the minimum year is 2000 and the maximum year is 2012. So by this information, just this 2000 alone kind of tells you that it's unlikely that a car has been for sale for 12 years. This is probably going to be the manufacture date. So just by examining the data, you're able to come up with certain inferences. So let's see what else we can find out from this set of data. Alright, so let's begin with a summary of the year and examine what types of statistics we actually get. So we get the minimum number, the first quartile, the median, the mean, the third quartile, and the maximum. So the minimum and the maximum are pretty clear. They're the most extreme points. The median is the middle point of the data, and if it's an even number, it's the average of the two middle points. The mean is the total number of observations summed up divided by the number of observations, and the first quartile is the value after 25 of 25% of the data, and this is the value at the 75 percentile of data. So similarly, for price and mileage, we can look at the these values, we can see that there's a possible outlier with price of 3,800 and in terms of the mileage as well. But if you look at all of this data, you can see that the median is the data probably has a somewhat normal distribution. But we'll figure out if it does exactly later when we start plotting it. But this gives you some meaningful insight on how the price correlates with the mileage in terms of just a qualitative standpoint just by looking at these numbers. Alright, so let's begin talking about ranges. So if we, to just get the minimum and maximum value for, say, used car price, we can use range, which will give you the two extreme points of minimum and maximum. And you can take the difference of this to get the range of the data. It's about is, say, susceptible to outliers. Or you think it is based on what you've seen. You can use an interquartile range, which is the 75th percentile of which is Q3, subtract the 25th percentile, and this should give you an indication of the interquartile range, and that's about 3,900. You aren't just limited to quartiles. You can split the data in other ways too. So let's use the quantile function on used car price, and this will create 5 bins, or not 5 bins actually. It'll give you the values at the percentile of 0, 25, 50, 75, and 100. So you can also get the probability or the value at a distinct percentile, so the 1 percentile and the 99 percentile, and you can use this and you can see the 1 percentile and the 99 percentile as well. So let's say you want a different range. Let's say you want to increase it by increments of 20. You want the values at the 20th percentile, the 0, 20, 40, 60, 80, 100. So you go from 0 to 1 by increments of 0.2. And that's the sequence. And you can look up what the actual description of this is by using the question mark quantile, and you can actually see what the arguments for this function are. But let's run this. And as you can see, you get what you want at the 0th percentile, the 20th, 40th, and so on to the 100th percentile. So now we're going to delve into a little bit about how this data is actually ordered. We're going to be plotting and then discussing some statistics. So the first type of plot that we're going to be using is a box plot. So let's examine a box plot. Let's plot price against the used car price data. So let's look at this plot. What is this plot actually telling us? Well, it's a box and whiskers plot. So the horizontal line here represents the median value, the median data point. This is the first quartile, and this is the third quartile. And finally, these end points here are 1.5 times the minimum value of the first quartile value, and 1.5 times the third quartile value. All these data points that are left over they could be outliers because they're not held within 1.5 times this range. This gives you an indication that there might be a skew, but we'll get into that a little bit later. All right, so if we plot mileage, as you can see here, you can probably notice a trend. There's probably going to be a skew here because 1.5 times, there's a lot of data points above 1.5 times the third quartile. So it would be interesting to look at histograms at this point, given the visualization of this data thus far. Histogram. The way histogram works is it creates bins and then measures the frequency of observations within those bins. So let's say 0 to 2,500 price, how many observations are within this range. So let's look at used car prices. We can see that there's a slight left skew, as we could kind of tell from the box plot. So as we recall from the box plot of the car mileage, that there was a lot of data above the third quartile, 1.5 times. So, and that's seen here with this really pronounced right skew. It just shows you that there's very few cars listed at the higher odometer readings, and that's basically what you're going to see with this data. Most of the data is contained. So there's two types of distributions that we have to understand, as well as some basic statistics in order to move forward. The first type is a uniform distribution. Things that have a uniform distribution are simple things like rolling a single dice. Every side of the dice has an equal probability of showing up. But most things that are observed have a Gaussian or bell curve or normal distribution. So if we look here, even summing up two or more dice causes a normal distribution about the mean. So two dice, the mean is about 7, and the probabilities of rolling a combination of two is normally distributed. And this trend continues to increase as you increase the number of dice. So as I mentioned, the middle point is the mean. So the variance is the sum of all the observed values in your set minus the mean of the population, and you square that. The reason you square that is because positive and negatives cancel out if you don't square it, so that's partially the reason. So you square that and you divide that by n, and that'll give you the variance, and the square root of that will give you the standard deviation. Now the standard deviation is important because it gives you an idea of how the data is distributed. So from -1 sigma to +1 sigma is about 65% of the data, and about 95% data within 2 standard deviations. So most of the data lies well within the middle parameter, and by 3 standard deviations you have almost 99.8% of the data. So we can calculate the variance and the standard deviations for the price as well as the mileage, but as we noted, there is a skew to the data, and also this is not a complete population, it's just a sample, so the equations I told you before are slightly modified for samples. So you have to be very certain about the type of data that you're analyzing, but it never hurts to actually check some of these values, especially when it comes to interpretation. So let's look at creating bins based on categorical variables. So we have year, model, and color. We can actually tabulate all of those, the number of observations within each. So if we look here, we can create, there's 3 cars that were manufactured in 2001 and 2001. And so with the models, you can see that we have 78 of the SE model, 49 of the SES model, and we also have similar bins for all the colors. We can also assign this table to, say, model table, and we can get the probabilities associated using prop table, and that'll give you, so for the models, there's 52% are the SE, about 15% are SEL, and about 33% are SCS. So we can also model relationships. One would assume that there might be a relationship between the mileage and the price based on background that you have with cars. So let's create a scatter plot of price versus mileage, and we can draw inferences of what type of relationship this has. We'll put the odometer reading on the x-axis and the price on the y-axis. And what we see here is what you would probably expect. As the mileage increases, the price decreases. So we observe a inverse relationship between the two. There are some. We'll talk about noise and bias, various trade-offs a little later on in terms of overfitting your data, but something like this shouldn't really affect a model that you're building when it comes to machine learning, and we'll talk about tactics to avoid overfitting noise. So the last thing we want to examine is cross tables. So you're going to install the Gmodels package as well as the library. I think I already have it installed, so it should work regardless, but if you haven't, please do so. So let's look at cross tables. Cross tables are particularly useful for comparing different types of variables such as models versus what you deem as a conservative color versus not a conservative color, and seeing how this data correlates or fits with each other. So using our real world experience, we know that certain colors are conservative, like black, gray, silver, and white, and certain colors aren't. Let's examine this piece of code backwards to better understand it. First, we're going to create a combination of black, gray, silver, white, which we believe are conservative colors. And if these colors are in used car color, then they will be added to the subset of used car conservative. All right. Now you're gonna have a table which is basically going to give you if the number of that that's true and the number of that that's false. So the table will say that there's 99 cars in total, regardless of model, that have conservative colors, and 51 of them don't have conservative colors. Now let's see how that varies with each model. So here we can see the result of the cross table. We have X being the used car model and Y being the conservative values. So the SE model has 27 non-conservative and 51 conservative colors, and there's a total of 78. Similarly, there's 7 non-conservative colors in the SCL and 16 conservative colors. So you can compare and contrast how these relationships change with two variables like model and color. While the implications of this are not particularly apparent right away, you can actually use this in terms of validating a predictive model. If you subset 50% of your data to predict another 50%, or you've created a model that's going to predict real life, how accurate is that model? And you can check false positives and false negatives. And we'll be doing that in the next chapter to see how well our nearest neighbor model predicts if breast cancer tumors are benign or malignant.